Okay, so I know I'm the last one keeping you away from lunch, so I try to make it brief. I wanted to talk about ImageClair, which is image annotation challenge, and there was a team of people involved very closely with that. I'm just one of them, and I will report here. So ImageClair, I actually recently realized that not many people know what it is. It's been running for like 15 years now, and this is very European initiative, and it's basically associated with conference and labs of the evaluation forum, and they organize various challenges, and one of them is in image annotation. So image annotation is basically generating benchmarks and then evaluating different teams. So this year there were 4 tasks, main sort of tasks. Sometimes those tasks change over years, and this time there were image annotation as usually, and then medical classification, medical clustering, and some liver CT annotation. So the schedule of this challenge is actually very recent. So you can see we started in February. We obviously started last year, but we released first data in February. Then in April there is a submission of the results. People register way before actually when it happens. Then in May we have basically participants submitting their runs. In June, so you see very recent, they actually we release processed results, put it on the websites, and then we receive submission of working notes from the participants. So I was basically getting that over the last few days and trying to compile a few slides for this presentation. So there were 2 tasks within the image annotation. The first one was quite standard image localization detection, where we have images, and the machines are asked to actually annotate with bounding boxes and labels where the images are. And that was for 500,000 images, and the task was to annotate, localize 251 concepts, so labels. And then as a teaser, we ran first time the tasks 2, which was about generating sentences for 500,000 images. And that was done for 2 tracks, noisy track, so that means we start from the image and some documents, text documents, and we want to have a really clean caption for the image. And then there was the second task for people that are not familiar with computer vision processes, for like NLP people, where we were giving the perfect detections in the image, perfect outputs of classifiers, and they were asked to actually generate sentences. Right, so to get the data for this kind of tasks, we run through 5 different stages. So first, concept selection. So we were selecting these 251 labels. Then image document selection from the websites. Image level annotation, so bounding boxes, labels, and then textual description in terms of sentences, so all those. So the 251 concepts were actually quite difficult to select, but they vary a lot from, for example, airplane, bottle, face, arm. And then we formed them from word occurrences from 34 million web pages, all in English. And actually, the web pages were retrieved by Google searches from for all words in English dictionary. And then we trained CNN classifiers on images like Pascal, and so we could actually filter out some images that are not very interesting for description, like this one, for example, and try to find more natural images. So we ranked the images, those 40 million, and then we picked 500,000 images and made sure that there are at least 20 images per concept. Then we selected a subset for evaluation, development set, nearly 2,000 images, and test set 3,000 images for the 2 sentence generation tasks. And all that was annotated using Crowdsource with bounding boxes and also with sentences. So I'll just give you an idea how we did it. So we first asked to actually point what is in the image, all right, without specifying where it is. And it's not just saying the obvious things, that there is a man, but also going down to details like indicating that he has guns, 2 guns, legs, hands, head. There is some water below. There are mountains, islands, and so on. And they could indicate groups of objects. They could indicate instances of objects. And once we collected that, so we made sure actually that this is properly done. This is really well done. People were well trained to do that. Once we had it, we ran another crowdsourcing exercise on different actually system. For us, it's quite tough to use Amazon Turk and all the other kind of crowdsourcing systems due to some finance problems. I mean, how we can spend money on. So we have to be careful which websites we use for this. We use Crowdflower in this case. And we displayed the objects, the number of objects that were annotated in the previous stage, and people were annotating with the bounding boxes, and there were several stages of this to refine, you know, to get it as accurate as possible. So then we, once we had now the bounding boxes and labels, we asked in the next stage people to actually generate sentences for the images, and we also used Crowdflower, and we generated a minimum of 5 sentences per image. Up to 51 sentences, and then we ran some basic spell corrections. We kept both American and British spelling and so on. So on average, we ended up with 9 sentences per image. We obviously gave a lot of indications, you know, guidelines how to generate a good sentence. We also gave examples. What is a good sentence? What is a bad sentence? For an image, like in this case, Pretty Woman, it's not descriptive enough, and so on. So people were trained, and then they were annotating. And here's an example. What we get: an image, annotation, bounding boxes, and sentences. And then the final stage was to actually align objects from the sentences with the image. So we could also run some other evaluation on the results. Okay, so that's the data, all right? That's how we generated. The difference is actually to what you well known from like Pascal and ImageNet and now Coco is that the training data is really quite noisy, and the data is not just images from which you generate. The data is actually image with associated text document, which is online somewhere, a website, all right? And the website has a lot of links to other documents, may have other images. Okay, so there is much more information, but it's very noisy information as well. So the task is really to generate recognition, natural language description based on images, but also on the associated text with those images. Okay, and the test is set on 500,000 images. So in addition to this data, also to you know, allow people, more people to actually participate, those that don't have processing resources, those that don't have expertise in computer vision, we also released features for the images, so standard features like CNN, GIST, histogram, SIFT, various packs of words, and also text features. So a list of word score pairs, triplets of words, different ranks from search engines for those words, URLs for images that sometimes actually have names, also within the URL, also URLs for associated images with the web pages. So there's quite a lot of additional information, but this is still, you know, the task is still quite challenging. So just to recap, so there are 2 image, first image localization detection on 500K images, and then subtask 2 is noisy track and clean track on generating sentences. Okay, the evaluation protocol for the first one is we allow people to submit up to 100 localized labels, concepts with bounding boxes, okay? And then we calculate standard measures like intersection of a union for the localization. And we also generate confidence thresholds. We run the confidence thresholds to actually generate curves for the detections. So the results, first I give you for the basic labeling, okay, of the objects, and then on the sentence generation. So the names of the teams won't tell you much here, so I just put the top 2 on the right. The result the results are actually quite good in terms of zero overlap. That means this is the classification. Okay, basically we ignore the actual location in the image, and this is with the 50% of overlap on the bounding boxes. So we are looking really on the accuracy, how well those systems work. The top results are pretty good. I'll tell you in a minute what are the methods, then you go down. We had like 20 teams, I think, submitting different results. So this is not the full list. It looks like if it does well in classification, it does well in the actual object detection, with some actually changes in the ranking lower in the level. So. If we look across the accuracy, so this is the overlap, how well, the ranking is more or less the same, all right? It doesn't change between the methods. So the two top methods are actually the same as they were before, 2-3 top methods. Okay, obviously the performance goes down as we expect more accuracy. So that's one. Another thing we looked at is which concepts were actually detected more easily and which were the tough ones. So things like B, surprisingly, the mobile phone, the telephone in general, fish were quite well detected, even if the occurrences were pretty low. Then the tough concepts were temple, wheel, letter. So well, maybe these examples will give you some better idea. So these are B. Okay, this is the telephone. So these were the good, actually, concepts. The weak ones were wheels, which are somewhere here. Okay, so the problems are occlusions here, and temple somehow maybe it was misclassified with something else. The method actually that worked well is quite standard. This is by one team. The training is illustrated here. So I've seen that really a day ago, so I don't know a lot of details. But basically, here is based on the concept, they do additional search. They download images, perform some filtering, and train standard CNN with GoogleNet, okay, on the given concept. And then given those classifiers, okay, they run object proposal, R CNN-like method, okay, classification, then non-maxima suppression and fusion. I'm not sure what's morphological learning, but the additional pipeline that they used was for face and gender detection on body part as well. So this is augmenting somehow the results from the standard pipeline. Okay, so that's one method, and the second method was actually quite similar. Also, the trick is to run two pipelines, query image, annotation by classification, and then a web page description. So this is based on the text in the web pages, and additional annotation by just doing additional search with different engines. Okay, so it's like two-stage approach. More details are on this slide, but it's really beyond me to explain that. So I just skip and move to the next one. So another problem that we looked at, okay, was this. So that previous one was just localization, bounding box detection, and labeling. Another one was the sentence generation, which is the interesting one. And for that, we used the Meteor measure, which is quite widely used now. And there were two tracks, as I mentioned. One is clean given bounding boxes. So the clean track is given the bounding boxes with labels, okay? People were asked to actually generate the sentence. So once you have the perfect detection, perfect detector, how well can you generate the sentence? And this has actually some difficulty. It's not just putting some surface realizer on the top of the objects. You have to select also what are the relevant objects, what is the important thing. And we wanted to measure that as well, because the annotation includes a lot of details, okay? Boots, legs, eyes, maybe nose for that person, which you normally wouldn't describe in the sentence. So we tried to measure that with basically precision recall, okay, where recall is actually intersection between the standard sentence remember, we have the sentence and we have the words in the sentence aligned with the bounding boxes. So we know actually which corresponds to which. We can then, given the generated sentence, we can actually measure what is the intersection between the generated and the gold standard, all right? And we can get the precision and then F-scores for this as well. So the results for clean tasks, okay, were by actually different team. The score were better than for the actual label annotation. So that's quite interesting. Mean precision is 0.7, which is quite high. Okay, recall is a bit lower, all right, it's on the level of less than 50%. And then the second one in the ranking is a bit lower in both, but it has higher recall than. But this is given perfect detector, okay, almost entirely relying on some NLP techniques to build the sentence. Sorry, that was for the selection of the contents. This one is actually for the generating the sentence. So once we have the labels selected for generating, how well they generate the sentence, so it corresponds to the ground truth. Okay, and with Meteor, okay, the score is, the top score was 2.24, okay, which is not bad for that kind of measure. And the next one was 0.2. All right, so these were the clean tasks. Now the noisy task, which is the more interesting thing. So given the image, how can we from the scratch, you know, and the associate text, how can we generate the results? So the results are obviously much lower, much more noise there. At the baseline, okay, we run the baseline sort of system, which is the Google-like CNN using VGG network, I think, and then LSTM for generating sentences. And that gave a score of 1.5, okay, with Meteor. And then those two methods did a bit better, okay? So the interesting thing was to look at what they did to actually achieve a better score. And it might be a bit disappointing, but the actual key was to properly collect the data, okay, or to get more data even for annotation and for learning, for training. So the pipeline is again standard, okay, CNN features, LSTM, RNN prediction, and then generating the sentences. The additional thing that they do is this concept detection. For some difficult concepts, they had another parallel pipeline where they were actually improving the accuracy in the sentences, so adding some adjectives and that type of things. Otherwise, this is fairly standard now pipeline you could see in some of the oral talks. Okay, all right, that was quite quick then. All I have left just to summarize. All right, so we have this new data and new challenge for image caption generation, which is actually different from what you know from Coco now and from Flickr 30K, and close also to so slightly different application, okay, because you can also use text documents, so as they naturally actually occur in the internet. And this is also open for NLP community where people don't do image recognition, so that hopefully will be useful too for them. And for this year, we used 500,000 images for test, and then some of them were annotated. We will be growing the annotation, growing the development set in future, so hopefully it will be more and more interesting. Okay? Okay, thank you.